There is an intimate connection between a rate law for a reaction and its mechanism, and this video is all about how we go from a mechanism to derive a rate law. So this one is probably the most central video to all of the things that we're going to do in this last module. So our learning goals are how to derive the rate law from the reaction mechanism. Now, to start with, we're going to make a bold statement about elementary steps. You may recall when we were talking about the rate of chemical reactions that I said you could not actually write down a differential rate law for a reaction until you'd done an experiment to find out what that rate law was. And the reason for that is that we don't know in advance if a given reaction was a complex reaction or an elementary reaction. However, if it's an elementary reaction, then the rate law always is derivable from the balanced chemical equation. And in particular, the rate law would look like K times the concentration of A raised to the power of its balanced chemical equation coefficient times B raised to the power of its balanced equation coefficient. So whenever we have an elementary step, that is a step that goes only over one transition state, we can automatically write down a rate law for that step. Now, there are a limited number of elementary steps, and I'm going to give you the three that really are the most common. Okay, first type of elementary step would be a single molecule, A, that goes to products. So it may be falling apart or maybe rearranging. It's doing something, but it's just one reactant molecule, in which case, according to this rule, the elementary rate law would be K times the concentration of A. Now, we might also have a case where we need two A's to collide with one another. Maybe that gives it enough energy. But in any case, the elementary reaction requires two of them to come together in order to make products. And in that case, the rate law is going to be rate is equal to K times the concentration of A squared. All right? If we look back at the general form, it has to be raised to the coefficient of it, that it appears in the balanced chemical equation. And in this case, that's 2, so it's A raised to the second power. The third one that we're most likely to see is a collision between two different molecules, A and B, and when they go to products, the elementary rate law can be written as K times the concentration of A times the concentration of B. Now, why do I say this is the only ones we really need to worry about? Well, it turns out that the chances of three molecules colliding together at one time is so small that that generally doesn't contribute to most rate laws. So these are the three that really matter the most when we look at different rate laws. So now let's consider a complex reaction that's made up of two steps. And we're going to talk about this particular kind of reaction mechanism for a couple of slides. So pay attention to what we're doing here because we're going to use some of those results later. Now, I'm going to say that these two steps can be characterized as follows. The first step is a fast equilibrium. So it reaches equilibrium and it does so very fast. The second step is a slow step that produces product. So now, what I can get from this is that since equilibrium means that the forward rate and the reverse rate have to be equal to one another, that means I can write down something like this. Now in this case, I'm using K1 to represent the rate constant for the forward reaction, and K minus 1 to represent the rate constant of the reverse reaction. So the reverse reaction is going from B to A. The forward reaction is going from A to B. So the rate of the forward reaction would be K1 times A, and the rate of the reverse reaction would be K minus 1 times B. So these are just reflecting the various rate laws for elementary steps. So now if I rearrange this equation, for example, if I divide both sides by the concentration of A and I divide both sides by K minus 1, I can write that the ratio of the concentration of B to the concentration of A is just equal to K1 over K minus 1. But that ratio of concentrations is also equal to the equilibrium constant. So in effect, I've shown that the equilibrium constant is directly related to the ratio of the forward rate constant divided by the reverse rate constant. This is going to generally be true when we have a step in a mechanism that reaches equilibrium. Now let's move a little bit further with analyzing these elementary steps. So here again is our first step, the fast equilibrium, and here again is our second step, which is the slow step. Now from these elementary steps, we would deduce that the second step is the rate limiting step. usually the rate limiting step is going to be the slowest step in the reaction mechanism. If I had a whole bunch of different steps and a couple of them were slow, I wouldn't necessarily know which one was the rate limiting step unless I had a way to measure which one was the slowest of all of them. In this case, though, we can be pretty confident that the second step is going to be the slow step and therefore the rate limiting step. So now the rate of the overall reaction, since it's rate limited by step 2, it's going to be reflected by the rate of step 2. All right, now if I write that rate down using our rules for elementary rate laws, that would be K2 times the concentration of B times the concentration of C. But remember, on the previous slide, we showed that there's a fast equilibrium in step 1, so we can actually write the concentration of B in terms of the concentration of A. And it's going to be equal to K1 over K minus 1 times the concentration of A. Now, our net reaction in this case is A plus C going to D. Look at B, it's an intermediate in this particular reaction mechanism. So when I write down my overall rate law, I always want to write it in terms of reactants that appear in the net reaction. Okay, there's no legal procedure that gives us this rule, but in general, you want to always express your rate law in terms of the reactants that appear in the net chemical equation. So in this case, our overall rate law is going to start with the rate K2 times B times C, that is the rate of the second reaction. But now we're going to substitute for that concentration of B using that expression for A. So now our overall rate law for the reaction is going to look like this. The rate constant is somewhat complicated. It's K1 times K2 divided by K minus 1, and that's really just the product of the K2 that comes from our slowest step and the K1 over K minus 1 that helps us convert from concentration of B to concentration of A. But with this rate law now, we have a rate law that is expressed in terms of the reactants of the net reaction. Now let's think about what this means energetically. So I'm going to write down that first equilibrium, that fast equilibrium step. How would we draw a reaction diagram for that? Okay, this is a fast equilibrium, so it probably doesn't have a very high barrier between the two sides of the equilibrium. So I might draw a curve that looks something like this. All right, A is on one side, is in the well on one side, and B is in the well on the other side. And this would be fine. But now I've got another step that occurs, and that's when the result of this reacts with C to give our product D. And we need this step or we'll never get to the product D. We also know that this is the slow step. It's the rate limiting step. So we would expect the barrier for this step to be much higher than the barrier in the equilibrium step. So there's nothing exact about this, but if I were to draw the curve, I might draw a big barrier there to indicate that this is going to be the rate limiting step. And that rate limiting step is set by the fact that the activation energy is the greatest for this particular step as we're moving forward. So the reactants have to go over this transition state, so they have to surmount that activation barrier in order to get to the products at the end, and we got reactants and products here. To get to the products at the end, we have to get over that high barrier. So I want you to be able to think about these reaction mechanisms that were given and think about how you might draw a reaction energy diagram for them based on the clues that you're given in the mechanism itself. Now let's do an example. We're going to find the rate law for synthesis of NOBr from NO and bromine 2. And it's hypothesized that this occurs via the following two-step mechanism. The first step has NO plus Br2 goes to NOBr2, and that's a slow step with a rate constant of K1. The second step goes from NO plus, is a reaction of NO with NOBr2 to form two NOBr molecules, and that we'll say is a fast step with a rate constant of K2. So now if we add up these two reactions, we would find that the net reaction in this case is 2NO plus Br2 goes to 2NOBr. Now what I want you to be able to do is recognize what is the intermediate in this case. If you look closely at this, there's only one species that doesn't appear in the net chemical reaction, and that's NOBr2, so it is an intermediate. That means we don't want it to appear in our ultimate rate law that we're going to derive for this particular reaction. Now I also want you to be able to draw a reaction energy diagram for this. Now the first step is the slow step, so it's the one that should have the highest barrier. So if I draw a curve that looks something like this, I might be on the right track. So once again here, the activation energy for that first step is the largest step, so it's the slow first step, whereas the little bump that occurs after that is the barrier for the second fast step in this particular mechanism. The rate of the total reaction is going to be the rate for getting over that first barrier. It's the rate of the first step. So if I were to write that down using the elementary step that's step 1, I would write it as K1 times the product of the concentrations of the two reactants in that step, NO and Br2. And this would be, in fact, the overall rate law for the total reaction, because those two species happen to be in the net equation for the reaction. So that means that our overall rate constant is very simply given by the rate constant for the first step. Now this has been a little bit of an easy application of it, but I hope it's given you some idea of how one can use a mechanism to derive a rate law.